Hello, warm greeting and welcome to all in this session. And today I'm going to present on these multiple integrals on the topic these double integrals and their applications to real and area and volume. So from Riemann sums over rectangles to general regions and polar coordinates, evaluating area and volume with double integrals. So without delay, I would like to proceed in this session. So okay, so what we will explore then? So apart from the definition of a double integral to its use in measuring area and volume. So this integral can be double integrations also we can say. So this can be used for this both area and volume measurement or calculation. Now from Riemann sums to double integral. Here that's the partitioning a region and summing infinitesimal volumes. Now, Fibonacci theorem next. So covering a double integral into two ordinary integrals. In this way, integrals over general region, extending rectangles to regions bounded by curves. In this way, applications of this double integration, so area and volume, especially we'll discuss over here, and the setting that f is equal to 1 for area. So this that fxy multivariable for volume under a surface. Now polar coordinates handling circular and the radical regions with the dh equal to r dr d theta. So okay, for the next, so from Riemann sums to double integral. Now here partition a rectangle are into small sub-rectangles like this in this picture. That is del A or delta A on E is from a thin box of height that's f xi y yg. We can just uh, see in the picture and sum the volume, then it gives the double summation of xij comma yij del A. So here as del A tends to 0, the sum converges to the double integral, such as we can express like this double integral for r. So fxy dA. So geometric meaning when fxy is greater or equal to 0, this is the volume of the solid lying between the surface z fxy and the region r. So in Fibonacci theorem, so turning a double integral into two ordinary single variable integrals. So we can express mathematically. So if f is a continuous on the rectangle R, such that such that a is smaller or equal to the x, or is smaller or equal to b, then c is or y is greater than or is equal to c and smaller or is equal to d. Then so double integration r fxy d is equal to the integrations a to b, the integration fxy dy dx. So it is equal to the double integration fxy dx dy also. So we can change the words like this. So inner integrals here we can see this y is greater or equal to the c or less than or equal to d. In this way, inner integral over here or a is x is greater than or equal to a or smaller or equal to b. So here, number one, fix the outer variables at first. So treat it as a constant while integrating with respect to the inner variables. Number two, evaluate the inner integral produces a function of the outer variable only. So integrate the result now. So evaluate the remaining and the variable integrals over it. So okay, for the next now. So here worked out examples. So integrating over rectangles now. So evaluate that is the integration 0 to 3 and integration 1 to 2 x square y square dy dx. Now here inner integral, that is y is in the inner, so we have to do for this at first. Now y, that is from the 1 to 2, so that's after calculating this, we'll get this, we have to replace with the integrations of this 1 and 2, and we have to calculate, and we'll get this 7 by x, sorry, 7 by 3 x square. So again further we have to do for the x, because now we completed for the dy. So now for the integration 0 to 3 dx, whatever we form here, 7 by 3x squared. So outer integral, that is for the x, so it formed 0 to 3. Now after calculating this and integrating this, we'll get these integrations as that 7 by 3 x cubed by 3 0 to 3. So while putting the value of 3, that 0 gives the 0 all, so it provides like this. Now final result is what? Now 21. Okay, so the next one, double integrals over general region. So this is the region. So you're extending a and to that next g1 x. In this way, dy here, that is, and g2 x. Now not every region is a rectangle. So a type I or one region lies between two curves in x. So that is the equal to the x, y, such that x is greater or equal to a or less than or equal to b. So g dash x here, so is exactly the what, smaller or equal to y, or y is smaller or equal to g2 x. Now double integration of fxy d is equal to that integration a to b and integration of xy dy and dx, where g1x is less than or equal to y, or y is less than or equal to g2x. Now a type 2 region swaps the roles of action y, like integrate x between two curves x is equal to s1 y and x is equal to s2 y, with y ranging over an interval cd, close interval cd. Okay, so vertical strip right waves from the lower curve to the upper curve at each x before summing across all x from A to then B. So okay, for the next. Now application in the finding area. So setting fxy is equal to 1 turns the double integral into a formula for area. Now area D is equal to double integration dA. Now work out example, area between two parabolas. Find the area of the region D bounded by y is equal to 2x raised to and y is equal to 1 plus x raised to. Now, intersection points here, after calculating, keeping the values over here, we'll get that exactly the -1 and 1. In this way, by setting up the integral now, so we'll get that -1, integral -1 to 1. So while doing the integration of these, we'll get that exactly while calculating over here. So integration of -1 to 1 x 1 minus x square dx. Now evaluating this, so we'll get that putting the values of this lower and upper limit of integration, so we'll get that 2, and that means 4 by 3 while calculating the final result of or area of this rectangle. In this way, application that means finding the volume. So when fxy is greater than 0 on a region D, and the double integral gives the volume of the solid that lies above the region D in the xy plane. In this way, below the surface Z, that is fxy. Now, the volume B can be calculated by using this double integration of D region, the region fxy D. For a type 1 region D, this becomes the integrated integral. Now, V is equal to fa to b and fxy dy dx, where y is greater or equal to g1x and smaller or equal to g2x. The shaded region, the shaded solid, right, it sits above the curve base region D and under the paraboloid. The next two examples compute the volume exactly like this. Okay, now examples volume under a paraboloid. So find the volume under z is equal to x square plus y square and above the region D bounded y is equal to 2x and y is equal to x square. Now by finding the intersection, so we'll get that. So x square is equal to 2x, so the values of x 0 and 2, it means so y lies or y is greater than x square or equal or less than 2x or equal. So I'll say while setting up the iterated integrals over here, the v is equal to f0 to 2, the integration 0 to 2, and the integration of x square plus y square dy and dx, where the y is greater than or equal to x square and less than or equal to 2x. In this way, the integrate with respect to y. So here, setting up all the that's values over here, whatever we calculated before. Then with respect to x also we have to calculate. Then setting the limits upper and lower and upper. So we get final answers or the volume of this paraboloid curve is exactly 216 upon 35 cubic units. Okay, for the next now, work examples volume under a plane. Now find the volume under the plane 3x plus 2y plus z is equal to 12 and above the rectangle that r that is 0 1 and by minus 2 3. Now, by rewriting the z that we got already, whatever here, and the positive throughout the r, that is z is equal to 12 minus 3x minus 2y. In this way, set of the integral, that is v is equal to, that's the reason that integration 0 to 1 and integration minus 2 to 3, 12 minus 3x minus 2y dy dx. Now, while integrating with respect to y, we'll get this. And again, we're integrating with respect to x and setting the value lower and upper limit of the integration. So we'll get final volume 95 by 2 cubic units. Okay, for the next, double integrals in polar coordinates. So for reasons with the circular or the radial symmetry, polar coordinates simplify both the regions and the integrand. So conversions. Now let's say x is equal to r cos theta, y is equal to r sin theta, so d is equal to r dr d theta. So here double integral in the polar form is that double integrations are fx y d is equal to double integration a to b f r cos theta comma r sin theta r dr d theta. That's the parenthesis theta from alpha to beta. Now, why the extra factors are over here? So a small polar rectangle spans delta r in radius and delta theta in angle, but its actual area is approximately so r times d delta r times delta theta. That's r further from the origin sweep out more area for the same delta theta. And this factor of r must always appears when switching to the polar coordinates. It's okay. For the next. Now, work out examples for area of polar region. Now, use a double integral to find the area enclosed by one loop of the four-leaved rows R is equal to cos 2 theta. Now, identify one loop. So, one petal transfer the negative 5 by 4 is smaller or equal to the theta, or theta is smaller or equal to the pi by positive pi by 4 with r is greater or equal to 0 or less than equal to cos 2 theta. Now, while setting up the integrals over here for the area A, so double integration r dr d theta over that region. Now, integrating with respect to r, so half integral cos square 2 theta d theta from that theta form, that is the minus pi by 2 to positive pi by 4. In this way, integrate with respect to theta again like before, then there is the 1/4 of the theta plus 1/4 sine 4 theta that evaluated also, that is negative pi by 4 to positive pi by 4. Now at last the result will get A is equal to 1 by 4 times pi by 2, that is equal to 5 by 8 square unit. So okay, at glance area and volume. So how is it? Now area. So area D is equal to double integration of the region of dA. So set fxy is equal to 1. The double integral simply simply totals the small patches of surface del A that tile the region D. This way. So Cartesian, so integrations a to b, the integration dy dx, where y is greater or equal to g1 and less or equal to g2. So polar, in the polar form, so double integration r dr d theta, that's where theta is greater or equal to alpha or smaller or equal to beta. So for the volume, so already we uh, discussed V is equal to double integration d region fxy dA. Okay, for the next, now the final takeaway of this. So we discussed about the definition. A double integral extends single variable integration to dimensions and summing in and then infinitesimal volumes over a region. In this way, Fibonacci theorem. So let us evaluate a double integral as two ordinary iterated integrals in either order for continuous integrals in terms of x and y. So integral regions, so type 1, type 2 descriptions extend rectangles to regions bounded by curved. The key is choosing sensible limits. In this way, area versus volume. So we talked before also. This way, polar coordinates the base for the circle or the radial regions where radius can be measured or calculated. So okay, much for your past minute.